first one. We're delighted to have Fermi Ma, who's going to speak about quantum commitments and black hole radiation decoding, which you might have thought sounded completely unrelated, but listen, find out.
Great, thanks, Scott. So this is going to be sort of a survey talk, talking about works of Harlow Hayden, Scott Aronson, and Zvika Brakerski. But I'll try to talk about it kind of from a new perspective that's based on some conversations I had with Sam Gunn and Alex Lombardi last fall. Also, this is hopefully not going to be a very technical talk. I think I only have like half an hour of content planned. And so hopefully we'll be out of here quickly. So yeah, I just want to start out with a question that I'm sure we've all asked ourselves at some point. What does black hole radiation decoding have to do with quantum cryptography? And luckily for us, this is actually answered in a paper of Zvika Brakerski not too long ago. Black hole radiation decoding is quantum cryptography. Yeah, so let's look at this title for a second. You know, I'd be wondering, what does this mean? And depending on your background, like what is quantum cryptography, right? And one part I haven't highlighted yet. What does it mean for these two obviously not the same things to be the same thing? So one goal of this talk, at least, will be to at least understand the title of Zvika's paper. Like, what does he mean? So a little more concretely, my plan for today is I'm just going to start with a bit of background on black holes. So just a bare bones recap of what we need to know to understand this computational problem. I'll talk about this radiation decoding problem defined by Harlow and Hayden. Then I'm going to write down a slightly different problem I like to call the radiation distinguishing problem. And from that, I'm going to draw a connection to quantum commitments. And 3 and 4 is going to be sort of an alternative view of Zvika's results. Right. So let's start with this. Actually, before I do that, it's going to be like abundantly clear in just a second that I don't know anything about physics at all. So here's a warning slide for that. And everything I'm going to say about black hole physics, I learned from reading chapter 6 of Scott Aronson's Barbados lecture notes. They're really good. And they're like a strict superset of everything I know about black hole physics.
I already see a mistake in the parentheses there.
Any mistakes? What's the mistake?
The mistake is that you may very well be copying my mistakes.
All right, well, let's get to it. So according to Scott, this is what a black hole looks like. It's like a big purple circle. That's the event horizon. And at the middle, singularity is like a fancy word for the center of the black hole. According to Scott, black holes emit qubits of Hawking radiation. Okay. So that's one thing we should know. And actually, every outgoing qubit of Hawking radiation is actually maximally entangled with some infalling qubit. So it has this partner photon, they're maximally entangled, and its partner is falling towards a singularity. Okay. And these black holes emit radiation, they're losing energy and therefore losing mass. And if you wait long enough and let enough of it radiate, eventually the black hole evaporates completely. And the one other thing we have to know about this radiation is that the emitted radiation comes out in a really scrambled form. So that means, at least for the purposes of this talk, for simplicity, we're going to think about the post-evaporation state. So if you let the black hole evaporate completely, and then you gather up all of the qubits of Hawking radiation it's ever emitted over its lifetime, we're going to think of that as basically a random pure state. Okay. And one consequence of taking this perspective as black hole like really scrambling information is that after about 1/2 of the black hole has evaporated, a little more than 1/2, at that point, the qubits of radiation that are coming out start to be like really correlated with the radiation that's come out before that point. Okay. In fact, we'll say that the outgoing qubits are maximally entangled with the previously emitted radiation. So this is a funny picture. Doesn't this violate monogamy of entanglement? Right, we have this one qubit of radiation coming out, and I've claimed that it's maximally entangled with this infalling qubit, but also maximally entangled with all the previous radiation. Yeah.
Really simple thing. How can you model as a pure state when it's maximally entangled with an infalling qubit that's behind the event horizon? It's not.
Well, I mean, globally it would be a pure state.
If you
Right.
include the infalling qubit.
Yeah.
Okay.
So the physics answer to this is something called black hole complementarity by Susskind and Tuft. And this says that, well, if this outgoing qubit is maximally entangled with two different systems, one outside the black hole and one inside the black hole, then actually they're not two different systems. They're actually two different perspectives of the same system. So that's fine, but turns out there's still a problem even if you accept this, or it still seems to be a problem. And this is this paper on something called the firewall paradox by Almiri, Morolf, Polchinski, and Sully. They gave a thought experiment in which it seems like a single observer can actually detect this monogamy violation. So if we really want to understand black hole complementarity, we have to kind of sort out what's going on with this firewall paradox.
Sure. Can you recall why it's maximally entangled with both of them? With both of these red set and with the one that's...
Yeah, so the entanglement with the infalling qubit is, I guess, a prediction of quantum field theory. I don't really know more to say about that, but there's apparently maximally entangled. Like we would expect to see a bunch of EPR pairs that straddle the event horizon. And the guy on the inside, because he's inside the event horizon, is kind of stuck there, is going to fall towards the singularity. And the guy on the outside sometimes just shoots out. And so this prediction that you have a bunch of EPR pairs around the event horizon is kind of, I think, what quantum field theory says you have in a vacuum space. And for the, so that's that guy. That's this guy. And this one is just a prediction or a consequence of modeling the global state as a random pure state. So if you think of the global state of all n qubits of Hawking radiation that will ever be emitted as a Haar random state, the claim is that if I trace out a small number of qubits, actually up to about half of them, the resulting state is actually still kind of a random pure state, and those have lots of entanglement. So this one is sort of a quantum information prediction. And this is a quantum field theory prediction. Does that answer the? Okay. So what is the AMPS experiment? Well, the idea is that Alice is going to set up a black hole. So she's going to actually set it up in a state that she knows even. And what she's going to do is sit outside the black hole and basically set up a bunch of photodetectors all around the black hole to collect all of the Hawking radiation that it ever emits. And she's going to do this for a really, really, really long time. She's going to do this until 2/3 of the black hole has evaporated. And then at this point, she's going to use a quantum computer to sort of check, detect this entanglement that she expects to see, that is expected to be there between the next outgoing qubit of radiation and all the radiation she's seen so far. Right? As I just argued, right, we expect this qubit to be maximally entangled with this bunch of qubits. And all Alice is going to do is process these qubits through her quantum computer. And it's going to do something to these qubits and sort of arrange them so that the leftmost qubit here, this blue guy, is maximally entangled with the next qubit coming out. And we guarantee, we're guaranteed that this, doing this is possible. Right? We know that these are actually maximally entangled, so it is possible to do something to this side that'll turn this into an EPR pair, 0, 0 plus 1, 1, with this next outgoing qubit. Okay. So she's going to just check that these guys are maximally entangled. And then after doing that check, she will just jump into the black hole. So she carries her qubit in with her and then searches for the partner qubit and checks that those are actually maximally entangled. And she's like, whoa, that shouldn't happen. So I think in the original AMPS paper, what they propose is that, well, if you really want to keep believing in like our modern understanding of physics, which we expect to apply around the event horizon of a black hole, then there's got to be something breaking that entanglement between the outgoing qubit and the infalling qubit. And breaking this entanglement will release energy. So they predict that that there's got to be some kind of firewall right outside of the event horizon, like breaking all of these EPR pairs. And I think that a lot of people found this sort of unsettling, that this notion of like that a firewall would appear right outside the event horizon is kind of doesn't really line up with what we expected to happen at the event horizon. So fast forward a couple years, Harlow and Hayden proposed a very different resolution to the AMPS paradox, not based on firewalls, but instead based on computational complexity. And I think this is very cool and surprising. So what they said is, well, something is fishy with the second step of this AMP experiment. In particular, they argued is that under certain cryptographic assumptions, the second step, where Alice is running her quantum computer to process all this radiation and come up with a single qubit here, such that these two are an EPR pair, that this is actually a computationally hard task. That under certain cryptographic assumptions, this step can require exponential time. And exponential here is like exponential in some black hole parameter, like its mass, for instance. And so what that means, or what Harlow Hayden showed, is that by the time that she's actually done decoding, we'll expect that the black hole has like long evaporated, and there's nothing for her to jump into to observe this violation. Okay, so let me state this radiation decoding problem a little bit more carefully. So the idea is you're going to let C be some publicly known polynomial-sized quantum circuit. Okay. And we'll define the state psi to be the result of running C on the all-zero state. Okay. And we're going to think of psi as corresponding to the final state of all of the emitted radiation. Okay, so this is the picture. And we're going to further divide these registers into three kinds of registers. The first I'll call R for radiation. Actually, they're all radiation. We'll call this R, but this is for the radiation that's emitted so far. So this is the 2n over 3 qubits that Alice has collected, like while waiting for this black hole to evaporate. The next wire, the single qubit, is B. And this is just the next qubit shooting out of the black hole. And H is kind of everything else that'll come out later, but we're going to sort of ignore H. And the claim is that in the AMPS experiment, Alice is essentially doing the following task. She's given the R register of the state. She's not given the B and H registers. And she has to run some computation given just this part of the state that's going to output a single qubit, A, such that A and B is the EPR state 0, 0 plus 1, 1. Okay. And the promise is that this task is statistically possible, that R and B, like this R register and the single qubit B, are actually maximally entangled. So we know that this can be done. The task is just to do it. I'll pause for a few seconds and just let this sink in. Yeah, any questions on this? Yeah.
Well, you said the state was a random state.
Yeah.
Now you're using a polynomial this time.
Yeah, a little bit contradictory. Yeah, I guess what I'll say about that is that, and you're totally right. So the question was, I was saying that the output is a random state, and then I'm modeling this as a polynomial-sized circuit. So a few things. First off, I guess in the direction of like showing that this task is hard, we don't have to worry about that, because if we show that it's hard for like a polynomial-sized circuit, then I mean we should maybe be like extra convinced that it's going to be hard for like a true random state. I guess the other thing is that, and we also expect that like the black hole unitary is efficient, efficient in the sense of like polynomial in some like enormous parameter. So actually, the thing about it being a hard random state is also like a bit of a lie too. That like it's just like it's supposed to be very scrambled, but like maybe about as scrambled as you can get in a certain amount of time.
Right. No, I mean, nowhere in the firewall argument do you need anything to be hard random, right?
Yeah.
I mean, there's a certain point where you appeal to the scrambledness of the state.
Yeah.
So like say like what's going to happen at the page time, right?
Yeah. That's certainly going to be true for the output of like a poly-size random circuit as well.
Exactly.
So
Yeah.
what notion of scrambledness do you need?
We just need anything that will like, okay, the only thing we really need is that B and R are statistically entangled. Like that's the thing we concluded from the hard randomness, but you don't need, that's true for other states too.
So the qubit A is in R.
Sorry?
Qubit A is in R.
Yeah, R is like a scrambled version of the A qubit, right? So it's like, morally R is like A and B, but it's like scrambled, and your task is to like understand how they're scrambled.
When you say A, B is API, like the reduced state.
The what?
The reduced state.
Oh, like A is a single qubit, and I guess what you can do is when the adversary outputs this qubit A, you, like the referee or the person running the experiment, can just do a projected measurement on the 2-qubit state A, B, and check if it's the EPR state.
Okay.
Yeah.
So I have a more basic question. Like in the previous pictures, you show that these 2 qubits that are maximally entangled, they appear on the horizon, and one falls in and the other one escapes.
Yeah.
So like, why would the black hole evaporate? It should be getting bigger because there's all these green qubits falling in.
Oh, great question. Why would the black hole evaporate? Why are the green qubits are falling in? Anyone want to help me out?
I mean, if enough is falling in, then the black hole will never evaporate. But if you just imagine that stuff falls in at one time, and then it's left in a vacuum for all eternity, then eventually it will evaporate.
Well, I think the question was like, even if I don't assume that like nobody's like throwing anything into the black hole, he's asking if this thing falling in, right? Like, why doesn't this? Is that the question?
Yeah, like I mean, every time a qubit escapes, you're saying also a qubit falls in. So like,
There's
Isn't it 19?
no, it's actually. I mean, I was confused about the same thing. Right? Apparently, in quantum field theory, when there are these virtual pairs, it's negative energy that goes into the black hole, and it's positive energy that comes out of it. Although, I guess if you were inside the black hole and you saw that infalling qubit, it wouldn't look to you like negative energy. It would look like positive energy.
So should we really think of this as a qubit? As a qubit, the regular qubit?
It's a photon. It's a photon, right? Patrick, do you?
Help us.
I think your explanation was pretty good.
Yeah, but the question is, how does like a negative energy virtual particle go in from the external perspective, and yet from the internal perspective, there's a positive energy infalling particle. Are these just two different things?
Like, does the information increase while the energy drops?
I mean, energy is not defined in GR. It's the cheap answer, but
So the observer inside doesn't usually see an infalling qubit, because if you're an infalling observer,
Right.
you cross the horizon and you see vacuum.
Right.
It's because someone outside is accelerating relative to the black hole,
Right.
and so inside you don't really see anything.
But still, I mean, even with this explanation of energy, you still have more qubits. If I just view this as qubits, then why do I count only energy and not just the number of qubits?
Oh, well, that's part of the paradox, actually, right? But that's the question, right? This picture in which there are maximally entangled pairs get produced one after the other. From that perspective, it looks like the entropy of the black hole should just keep going up and up and up and up and up.
Right. Although also keep in mind that these infalling qubits, they're all going to hit the singularity, and then who knows what happens to them there.
Oh no.
Question here.
Yeah.
Can you just go back to
Yeah. This one?
Yes.
when you explain Harlow and Hayden. So what's the problem if by the time this is done decoding, the black hole has evaporated?
Oh, then she has nothing to jump into. Like the experiment, like the third step is she needs to jump in.
But that's like later radiation that you can potentially find the qubit in.
Yeah, I guess with the later radiation, like you won't find a contradiction there anymore. I think you won't find like another maximally entangled pair. Like once you wait for all the later radiation to come out, you're just staring at some like random looking pure state, random looking state. And if I'm staring at that, I'm not going to find a monogamy violation. I really have to like go in while the black hole is still there. Okay. Wait, any other questions on this? Questions are great. This is super confusing. So
Yeah, I'm a bit like you. I don't have any background in physics, but this paradox feels a little bit relativistic in the sense that what you show me is not saying that the paradox does not exist, but an observer cannot observe that there's a monogamy violation.
yeah, that's right.
Okay.
So I can, like, the general philosophy behind these things, right, is that, at least that, things are better understood now 10 years later. But at the time, people were proposing these thought experiments. And if there seems to be some paradox or contradiction in the thought experiment, that's potentially a problem for your understanding of quantum gravity. But if you find that there's an in-principle reason in the theory that you can't verify that there was a paradox, then that might be a hint that that the underlying theory does not have a problem, right? And so what this was about was saying, okay, well, it seems that there's this firewall paradox, right? It seems that there's this violation of quantum mechanics, violation of monogamy of entanglement. But if it's impossible in principle to ever verify that it exists, then maybe that's and we can then maybe that's a sign that there really isn't a paradox. Once we actually have the proper theory of quantum gravity, it just it shows that there is nothing to worry about. So that's sort of the philosophy thinking of these thought experiments and asking. It's the same idea as Heisenberg way back when, thinking about the uncertainty principle. He didn't start with the mathematics. He said, okay, well, I have this particle. I want to figure out where it is. How do I figure out where it is? I send in some other particle that's going to bounce off of it. And if I do that, if I want to really figure out to high accuracy where it is, I end up needing a high energy particle that imparts a lot of momentum. And so it was thinking through those kinds of thought experiments that led to the uncertainty principle, and then taught us that position and momentum are not independent. And so it's the same kind of philosophy here, trying to ask, what are the underlying restrictions on what you can actually know, so you can understand what the actual degrees of freedom and structure of the theory are.
Can I ask a follow-up question? Yeah. So as long as before this firewall paradox, there was this notion that the same observer cannot see a contradiction, and so maybe you can fold reality into two and say, well, these two are two versions of the same reality. But now, if you're saying, look, it's computationally impossible to, it takes exponential time to actually notice a contradiction. How do you, how would you imagine the underlying reality looks? You can't fold it, but what can you do with it?
Could I put a pin in that question?
Yeah.
Yes, sure. But it's a good question.
So I'll go to the next slide. I'll keep the radiation decoding problem up at the top. What Harlow and Hayden showed is that if BQP is not contained in a complexity class called statistical zero knowledge, so problems that admit statistical zero knowledge proofs, then
if SDK is not in BQP.
Oh, whoops.
Yeah.
Thanks.
Yeah.
Should have had a complexity theory disclaimer too. Then there exists some circuit C such that radiation decoding is hard. The way I should say, like, when asked, like, what is hard? And I think Zvika sort of pushed for this like more careful definition of like the probability threshold, where hard should really mean that no quantum polynomial time adversary can win with probability noticeably better than a quarter, because 1/4 is sort of your trivial win probability if the game is implemented by like the adversary outputs this qubit A, and then the challenger just checks whether it's the EPR state. And so that's a one state in 4-dimensional space. So if you're not doing anything,
because if you measure in the Bell basis, like the maximally mixed state, you'll get the right answer you want with
Yeah.
the quarter probability.
yeah, exactly. If you just output junk, you're going to win with 1/4 probability. So it should be hard to do better than that. Okay. Well, if you're making assumptions, and you care about the conclusions, well, you typically want to make the weakest assumptions possible. And later works did successfully weaken the assumptions you needed to conclude hardness of this radiation decoding problem. Scott, a few years later, showed how to argue radiation decoding hardness under the assumption that there exist quantum secure one-way functions, possibly injective one-way functions. I'm not really sure which one you needed. Okay. I found some slides that also did this, and I wasn't sure.
Oh, I think I did need injective.
Okay. Right. I think that maybe injective is incomparable to this. I'm not sure. I think like one-way functions would be weaker, but injective I think is technically incomparable.
Right, yeah. I think morally it's a much weaker assumption.
Right. Okay. Very recently, Zvika Brakerski got this all the way down to the existence of quantum bit commitments, which turn out to be a much weaker, or potentially much weaker assumption than the existence of quantum secure one-way functions. And I'll just say, like, the difference here is that this is a classical cryptographic primitive. This is like a classical function that's hard to invert by a quantum machine. But a quantum bit commitment refers to a quantum protocol, one where like you use quantum communication to commit to a bit. And in the recent progress in quantum cryptography, complexity has sort of pointed out that this is a potentially much weaker assumption, that like there is a world, like for instance, Oracle results saying that you might have a world where one-way functions don't exist, but still quantum bit commitments are possible. So it's a very weak cryptographic assumption. And turns out you're probably not going to be able to weaken it any further, because Zvika Brakerski also proved the reverse direction. So we showed that hardness of radiation decoding actually implies the existence of quantum bit commitments. So from an existential standpoint, these two problems are totally equivalent. And let me just emphasize like why cryptographers like really should care about this. The quantum bit commitments are not just this like one-off cryptographic primitive. They're really like this like central like workhorse of quantum cryptography. It turns out that quantum commitments imply, or actually are equivalent to, a bunch of other really central primitives like quantum oblivious transfer, multi-party computation, quantum zero-knowledge protocols for, say, NP or even QMA. And Zvika's words, not mine, this can be viewed as providing a physical justification for the existence of secure cryptography. So for instance, if you like really believe that Alice should not be able to trigger a firewall around the event horizon, and you like make a bunch of other assumptions, like you really believe that that like physics should hold true, that QFT and GR are true around the event horizon, then in some sense this is saying that like we can use that as evidence that there are cryptographically useful computational problems that are actually hard. So very different from the way we typically justify assumptions in cryptography, right? Usually it's that, oh, mathematicians have tried really hard for 50 years and mathematicians are really smart, so like if they haven't solved it, then maybe it's just hard. This is saying like maybe like there's actually like evidence from physics that some problems are just computationally intractable.
This is what do you mean by quantum bit commitments? We know that unconditionally secure, there's no go there.
Yeah, so this is an argument that computationally secure quantum bit commitments like exist. Yeah, like instead of proving like a circuit lower bound, it's saying like physics is telling us that actually it's secure.
Or maybe the truth is just that we can create the firewall. It just takes some, some non-trivial engineering that hasn't been done yet.
Yeah. So it's a win-win if you want to use firewalls. I don't know.
I mean, it's kind of like years ago, Seth Lloyd, said, his argument for the second, like P not equal to NP is that if P equals NP, then probably you could exploit it to create a Maxwell demon. Right?
Yeah.
And then we don't believe in Maxwell demons. Right? I think there are many steps that remain to be filled in this argument, but
I think that
similar flavor,
It's, there's still this like science wins either way flavor to this. So today, or for the rest of this talk, I'll try to explain like how this crypto connection works. I'm going to do it a little differently from how Zvika did it, and I'm going to go through this radiation distinguishing problem. So instead of like directly looking at this the original radiation decoding problem that I just defined, I'm going to define a new I'll call it radiation distinguishing question. So just to keep the old problem in mind, this is the decoding problem, the one where you're given R and you're asked to decode a single qubit A. But really, like the point of this problem, as far as we could tell, is that like R and B are guaranteed to be maximally entangled, but the problem is trying to capture the fact that this entanglement should not be efficiently detectable. And our reasoning is really that if this is the point of the problem, then you can write down a different problem that also, or that like very directly captures this point, only this radiation distinguishing question. So what we'll do is it's now a distinguishing game. So the adversary just needs to guess like which quantum state it received. Okay. So we'll have a challenger. It's going to flip a coin, and either it's going to give the adversary the actual R and B registers, the ones that are actually entangled, or it's going to replace the B register, this B qubit, with some unrelated maximally mixed qubit, B prime. So B prime is just not entangled with R. And the adversary's job is to distinguish which one it got. Right, so it wins if it guesses correctly which world it's in, and its goal is to guess correctly with probability better than 1/2. So how do these problems relate? Well, distinguishing is definitely easier than decoding, in the sense that if you can solve this decoding problem with advantage 1/4 plus some epsilon, then you can immediately solve the distinguishing problem with that same advantage. So the idea is just that, well, if you're in this world where you got the unentangled states, then if you run the decoder on the R part, then no matter what it does, no matter how fancy your decoder is, the chance that it outputs A such that A and B prime or the EPR state is exactly is at most 1/4. And on the other hand, if you run the decoder on R here, then you have a 1/4 plus epsilon chance. So if you just guess which world you're in based on whether or not your decoder succeeds, which you can check yourself, and you get a distinguisher.
Sorry, the decoding algorithm is using something that knows about C to do the decoding?
Something that knows about C. Oh, that's fine. I'm going to assume that you're given the full description of C.
In both?
Yeah, in both problems.
Okay.
In both problems, yeah. C will always think of as public. Like the only hardness is going to come from not having the whole state. Okay. At the same time, I claim that whatever arguments you make for physics saying that decoding is hard should apply like equally well to distinguishing being hard, right? Namely that like if Alice can't trigger a firewall, well, the point is that she shouldn't be able to detect any entanglement between B and R in the ants experiment. And we should expect that it doesn't matter to Alice if she's efficient, whether she gets the actual qubit B or some unrelated maximally mixed qubit B prime. So what's the point of writing this one down? Like, what do I gain by changing the problem to this? The claim is that this is already a natural crypto assumption once you look at it the right way. Like, at least in the Harlow Hayden paper, and and Scott's work and Zvika's work, you have to work a little bit. I mean, it's not too hard, but you still have to do something to engineer the crypto to fit the syntax of this radiation decoding problem. And our claim is just that if you write down this question, there's no engineering required. This is like already a useful and natural cryptographic object. So the rest of this talk is just going to try to explain like why that is. And the concrete claim is that radiation distinguishing is hard if and only if quantum commitments to the EPR state exist. So what I'll do for the rest of this time is just explain what that means. So what are commitments to quantum states? And then why do quantum commitments to the EPR state? Why are those the same thing as this radiation distinguishing problem? So really quickly, quantum state commitment is only very recently formally defined, but it's kind of been folklore for a long time. The idea is just that the sender is thinking of some quantum state, and it wants to commit to this. So the physical analogy is that imagine just the sender places its state in a box, locks it up, and sends that box to the receiver, and that's the commitment. And later it wants to open this commitment, and so it sends some piece of opening information, and the receiver takes all this stuff and verifies the opening is valid, opens up the box, and recovers the value, the state that the sender committed to. And we typically want some security properties, so you might ask for hiding and binding. So hiding would say that the commitment should hide the underlying message or state psi from the receiver. The receiver should have no idea what's inside it until it receives the opening. And binding should say that after it gets after the sender sends away the commitment, it can't change its mind anymore. It can't, commit to one state psi, commit, and then later be like, well, actually, I wanted to change that to some orthogonal state, for instance. So just two things we should know about committing to quantum states. First is that this requires computational assumptions. There's a well-known impossibility result from the 90s saying that when you use quantum communication to commit to classical bits, that already requires computational assumptions. And quantum state commitments are just a generalization to quantum states. But 0 and 1 are quantum states. So to do a quantum state commitment, you still need computational assumptions. And one more thing is that while the functionality is a bit more advanced, it's actually pretty easy to show that these are just existentially equivalent to quantum bit commitments. Namely, if you can commit to a bit and you want to commit to a state, what you can do is one-time pad the state, so apply random polys, and then commit to a description of those polys and send that along with the one-time padded state. So there's an easy way to go between quantum bit commitments and quantum state commitments. It's just that this abstraction is a little friendlier with what we're about to do. So the syntax here is that the way that you commit is that we just have a single unitary comm that specifies how the whole scheme works. And what the sender will do to commit is it just runs this unitary on the state it's trying to commit to together with a bunch of zeros. And then it splits up the resulting registers, the resulting state it gets, into a commitment part and the opening part. And so you send the commitment part to commit, and then you send the rest of the state to decommit later. And to verify, the receiver is just going to undo that unitary and then check if the last lambda qubits are 0. And it turns out that any commitment to quantum states, even an interactive protocol, can always be generically compressed to have this syntax. So this is a without loss of generality way to write any quantum state commitment. So for binding and hiding, what do they mean in this context? I'll look at statistical binding and computational hiding. So statistical binding just says that the commitment completely determines what I'm committing to. So when I send this C register, the state, that information theoretically determines the message that I committed to, the psi. So concretely, one way to think about this is that there exists some probably inefficient unitary that can recover the state psi from the C register alone. So if I just have C, there is some unitary I can apply that'll reproduce this psi state. And computational hiding says that no efficient adversary can distinguish whether it gets a commitment to a state psi of its own choosing or a commitment to a totally junk state. Okay, so in the security experiment here, the adversary gets to pick whatever message it wants. It can prepare the state however it would like. even like entangled with something else it holds on to. And then it sends that state to the challenger, and the challenger gives back either a commitment to that state or a commitment to some random unrelated junk. And the adversary's job is to tell which is which. And the crucial point is like really this indistinguishability needs to hold even if the adversary has a state entangled with psi. Okay, so like a natural setting to consider is what happens when you commit to the EPR state. So I have an EPR pair and registers A, B, and I commit to the A register. Well, statistical binding says that B, the other half of the EPR pair that was not involved in the commitment, must be maximally entangled with C. Right? This is just because C completely determines A. Right? From C, you could reconstruct A, so C must be maximally entangled with B. And computational hiding says that even if the adversary holds on to this B, it can't tell whether it gets a commitment to the actual A qubit, the one that's entangled with B, or it gets a commitment to some unrelated maximally mixed state. And one fun fact is that I can think of this equivalently, this B C prime state. It's distributed identically to B prime C. So you can imagine a world where the adversary gets like the B register is replaced by some other maximally mixed state, and it gets back the correct commitment to A. Like the point is that this is, in both cases, this B is maximally mixed and unentangled with C prime, which is a commitment to a maximally mixed state. And so when I put all this together, this is what it means to break the hiding of the EPR commitment. It's that you have these registers B, C, and D. You're promised that B and C are maximally entangled, and your task is to distinguish BC from B prime C, where B prime is an unentangled maximally mixed qubit. And just remember that this was the radiation distinguishing problem. They're exactly the same thing. That I just relabeled C with R. So if you have quantum commitments, then just like as an immediate corollary, you have hard radiation distinguishing. I mean, if you have quantum commitments, you can commit to any state. In particular, you can commit to the EPR state, and that means that this problem is hard.
Is it clear that if you have quantum commitments to some state, you can commit to any state?
That's the next slide. So this is for one direction, that if you have quantum commitments to all states, then you certainly have quantum commitments to the EPR states, by definition. One last thing, I need to show that, at least for the other direction, where I want to conclude that hard radiation distinguishing implies the existence of cryptography, I need to show that the ability to commit to the EPR state means that I can commit to any state. Yeah.
Actually, I guess also this is only showing that the radiation problem is like hard on worst case C, right? But like for black holes, you care about the actual C that comes from the black hole.
Really good question. Let me hold off on that, and I'll talk about that on my last slide. Okay. Yeah, but that same issue applies to sort of everything. Like maybe like even worse than the original like Harlow Hayden paper. That like there you're like really engineering a particular like C. By like planting this hard SEK problem there. Whereas there's like a lot more C's that we might expect to give quantum bit commitments or quantum state commitments. But I'll get back to that. Okay, so yeah, one last thing is just the ability to commit to an EPR state means you can commit to any state. So I have to justify this, and then that'll be the full equivalence. And I'll just say this is like a quantum-only thing. Right? Like in classical crypto, there's no theorem that's like once I can commit to 0, I can commit to anything. You really have to be able to commit to more than one thing. But there is this one particular state where if you commit to the EPR state, you can commit to anything. And the idea is if you can commit to the EPR state and you want to commit to a different state psi, what you do is you teleport psi into that C register. So to commit to psi, I'm going to measure psi together with this B qubit, and I'll measure it in the Bell basis. I'll get 2 classical bits, X and Z, and I send the EPR commitment C together with X and Z. And in some sense, you should think of this as like, this is like a scrambled version of like the teleported state, right? Like if the point is that C statistically determines this A qubit, and this A qubit together with X and Z, I mean, that's the result of teleportation on the other side, right? That I have A as well as these Pauli errors, and that's going to determine the state psi. And for computational hiding, we know that C together with X and Z is indistinguishable, computationally indistinguishable from C prime, where C prime is just a commitment to unrelated junk. And this is just something that is completely independent of psi.
Yeah. We'll teleport later, like send random X and Z, then teleport, and then okay, there will be some phases left later.
Then you just get the next state, right? Like you just get a maximum next state that comes out.
Oh, I see.
I mean, you could correct it, right? But that would be kind of allowing the adversary to break the commitment.
Yeah, like the receiver kind of knows how it's going to correct things, and if the adversary is like, actually today I want you to open the commitment differently, the receiver will know that something is up. If the receiver like follows the prescribed procedure for like reconstructing the original state, the adversary won't be able to change it. I can talk about that too. Yeah. Okay, so that's all I really had to say. Is the point of this talk is that there is a really like tight relationship between a certain problem in black hole physics and a natural question or natural like cryptographic primitive. And one last thing about Anand's question is, there is this choice of like C, the choice of this like black hole unitary that I was kind of vague about this whole time. It turns out that that's also a place where you have a nice connection between what you study in the black hole setting and what we'd like to look at in cryptography. So I think in the black hole setting, you typically model C as a random polynomial-sized circuit. And at the same time, I think like kind of in parallel, cryptographers are coming around to this view that when you want to commit to anything with a unitary, it seems pretty secure to plug in a random circuit for that unitary. But I think this is kind of one of the central questions to pursue in quantum cryptography, namely like just giving more evidence for the hardness of this problem. So I mean, people have been studying random circuits for quite a while now, but the kinds of problems that people look at, like these linear cross-entropy problems, it's plausible to me that even those problems like could end up actually being kind of easy, and this question of like breaking these like random circuit commitments might still be hard. So I think it's just a like fantastic question to give them better understanding, better evidence for hardness of these questions. And this is probably the simplest like way I can think of to write down this question. This is basically equivalent to all the computational problems I've stated so far. In particular, like just given a description of a random circuit, the question is like how hard is it to distinguish the output of the circuit on two orthogonal states if you're only given part of the circuit output, so 2n/3 of the qubits. So this is a setting in which the two states, the two mixed states you would see, are statistically distinguishable. And the question is like how hard is it to actually do this distinguishing? And so like one consequence of all this is like not only does this have like huge cryptographic implications to understand this question, but it's like very tightly related to understanding like the complexity of these same questions for black hole radiation. Okay, thanks.
Questions?
Okay, I guess that's mine. So we're saying that we can't detect this violation of the non-linear entanglement. But it seems like they're saying that's only close and make the black hole sufficiently large. We say it's exponential inside of the black hole.
Yeah.
It's still being detected, right?
Yeah, Scott has something like directly addressing this. I'll let you take it.
This question came up a decade ago, so I can tell you John Preskill's answer to it, which is that if the black hole is really microscopic, then we never expected, semi-classical descriptions to work for it anyway. So then there's no problem. Right. It's only when black holes get the macroscopic scale that we expected quantum field theory to work at all.
Does this view that C is a polynomial size factor come from physics, or is it part of the thought experiment? Because for example, some of the geometries we heard about this morning, I can imagine C would be logarithmic in that or exponential in that. you think there are interesting results in those cases as well?
I wasn't here in the morning. Patrick?
I mean, isn't it just the quantum extended church Turing thesis? You know, just the belief that like whatever is going on in a black hole, if you are outside of it, then you ought to be able to simulate it efficiently with a quantum computer.
Yeah, but
if that's false, that's a very big deal.
Fair enough. But the way Fermi said is just that the C comes from physics. So I just wonder if there's a natural.
I guess the idea is that you take whatever is the true quantum theory of gravity that governs the scrambling of the information, and then you simulate that using your Hamiltonian simulation algorithm, and that's what gives rise to your polynomial size circuit.
Let me be also more concrete. If I just said circuits of size log n, say, do you think that'd be an interesting cryptographic result in that case?
I think that there are maybe some lower bounds or some like upper bounds maybe on how secure this can be for log n size.
You
like
mean
certain
depth
architectures.
log n? Okay.
Yeah. At least like if it's like a Clifford T circuit and there's like only certain like T gates, I think that might even be the next talk.
Depth log n with 2-qubit gates only, but with no spatial locality, because like now all these things matter. Yeah.
So I have a question about this open question. So like in order to relate to the state commitment in a more straightforward way, I would have thought the right question would be distinguishing like C applied to all zero state and C applies to all zero state except one of the qubits in an arbitrary state psi.
Oh yeah, that's fine. Yeah, because I thought 0 to the n-1 concatenate 1 was ugly on the slide, but it's just two like different states that just starting with them being orthogonal. Yeah, they're fixed anyway. You know what they are, so it shouldn't matter as long as they're orthogonal. This is just me writing down like the property of being a secure quantum bit commitment. By the way, so they're bit commitment, state commitment, all sort of the same thing. So like easier to think about quantum state commitments when you're like writing down abstractions to connect things to the black hole radiation decoding problem. But when you're thinking about like the easiest like problem to write down, like the computational question, it's just this one.
Is there any like candidate argument for this? Because I've actually been asking this question for like many years, but I haven't gotten any satisfactory answers from anyone.
I don't know. I mean, you can try to give like oracle evidence for this at least. Like you could ask, I don't know, like how much you would believe like oracle evidence like sheds light on this question. Like maybe you can do a lot of fancy stuff when you have an explicit description of the circuit. At least in the oracle setting, like this seems very hard too. Like I give you oracle access to a Harlow unitary and its inverse, and I ask you like to distinguish these the same two things. Seems very, very hard. All I can say.
I mean, if we replace a random circuit by a different ensemble, then again, it's going to be at least as hard as breaking injective one-way functions or whatever.
Yeah. So I guess that together with some hypothesis that random circuits are the worst. Yeah.
Right. Like they only seem harder. But then, of course, it's hard to formalize that intuition. Anyone else?
How important is the 2/3?
Oh, not super important. It's just some parameter that makes the problem. You want to be in a regime where it's actually a computational question, that the two mixed states are actually statistically far. So like that regime is basically like pretty much everywhere between 1/2 and 1.
Yeah. If we allow 1, then this looks kind of like the Ullmann transformation problem from the unitary.
Yep, they're the same thing.
So that case was like when the fidelity between the traced out states is 1. So like they're the exact same.
Yeah.
And that problem was already unitary p-space. So like, which we think is really huge, right? So,
yeah, good. So the question is about like how this relates to this Ullmann transformation problem. It's actually, this is a question where you have like a pair of pure states, like bipartite pure states, and like on registers A, B, and you're promised that like their reduced densities on A are the same. And the task is that like, well, Ullmann's theorem says that applying just a unitary on the B side, you can turn one into the other. The question is like, how hard is this? That's like the swapping distinguishing dual of this question. Like if I take the sum of these, like if these states are hard to distinguish, like their sum and their difference, so like if you add them up, like versus subtract them, those two states like define like an Ullmann question.
But with that problem, like from Henry Yuan's paper,
Yeah.
Is there any assumption that the states came from a small circuit?
Yeah, I don't know exactly what they say about like the random circuit setting, but
Because that, I mean, that might explain why they go all the way up to p-space.
Yeah,
Right?
yeah. I think in that one, it's uniform in p-space circuit, so it's a lot bigger probably. Yeah.
Which paper are you talking about?
The recent paper
and
by
Henry Yuan.
Henry Yuan and students that did studies like the a bunch of problems with quantum inputs and quantum outputs, and like their unifying problem is this Ullmann transformation problem that Fermi just defined. Anyone else?
So if the circuit is actually not kind of sufficiently like randomizing to make things entangled, but only like things only look entangled, do you still get cryptographic hardness from that? So there was this work on like pseudo entanglement, right? That I think talks about this.
Sorry, so I didn't quite follow the question. You're saying
so you have like a statistical guarantee on the like that you know statistically that you can extract an EPR pair from this.
So you're going back to the decoding setup.
Yeah, exactly.
Yeah, okay.
Or whatever. Like statistically, you could distinguish. But maybe let's see. So I guess like there's a statistical binding and computational hiding, right? Is there like a computational binding variant that's like this seems maybe it's something to do with the actual entanglement?
Sorry, are you asking like can you switch the guarantees? So statistical hiding?
So you can switch the guarantees by like the flavor switching, right? But
Yeah.
I mean, like, is there an interpretation of the computational binding?
Oh, like for the black hole setting?
Yeah.
Like definitely for the EPR commitments, then you just have like a flavor switched EPR commitment. The guarantees are switched. But for black holes, I don't know. Question.
Yeah, I guess I don't have a very well formulated question, but like there's some, you could say, well, maybe this radiation is not maximally entangled; it just sort of looks maximally entangled.
Yeah, I don't know. Maybe. Yeah, I don't see like how to interpret that just yet. But maybe there's something there.
Yeah.
Yeah. Can you answer the policy question also? No.
Good. Sorry.
Anyone else? So, Fermi, do I understand correctly that like even if p were equal to p-space, for example, like we still would not know how to break all quantum bit commitment schemes?
That's a really good question. I think that I mean Will was asking me about something like I think Will has like some partial thoughts on this. I haven't thought too hard about the setting where you like explicitly have a description of the circuit. I think that yeah, I have more thoughts on what happens if you model this as a random unitary in an oracle. But when there's an explicit description, I would expect that there would be some kind of like complexity, like collapse that would make this easy.
Okay.
I just don't know what it is.
Well, okay. The reason I ask, like the main, and there's in my lecture notes in 2016, the main open problem I gave about the complexity of the Harlow and Hayden problem was actually the converse, right? I don't think you mentioned this, but like if I assume some computational superpower, then could I decode Hawking radiation?
Yeah. So I think that question is well formed in two regimes, right? One is like. For this question, like I explicitly give you a random circuits description.
Yep.
And that question is also well formed in like an oracle model too, where C is like a Har random unitary. And you still have to do the same problem. And your computational machine can answer like your oracle can answer any question about the Har random unitary.
Right.
And I mean the first one is a thing that I'm claiming that like maybe Will has ideas on.
Right.
The second I think is essentially the unitary synthesis problem.
Yeah. I see. All right. Maybe we'll talk with Will during the break. So, anyone else? So, You said you had a half hour of material, but as we learned from Patrick's talk, everything in quantum gravity is within a factor of 2. So let's take a break.